Okay. Recording. And let me share my screen now. Hopefully everyone can see my slides.
Yes, sir.
All right, guys. Welcome to Deep Learning. And I'm Dr. Vignesh Muralidharan. I'm an assistant professor at School of AI and Data Science. I'll be your instructor for Fractal 1. So it's a very exciting course and interesting course. There's a lot of interest in recent times in deep learning because of the recent sort of, literally uh, increase in the amount of artificial intelligence and AI based applications. So, where the foundational concepts come from deep learning, and we are going to learn some of these ideas, and hopefully, you can put them to good use in your field of interest, because these are tools, and you have to understand the tools and their possible areas of application, and then you can try and do it in your own area of interest. So before some logistics, course overview and evaluation. So contents that we'll cover in Fractal 1 are some basic introduction. We look at deep neural network models, specifically convolutional neural networks, recurrent neural networks, and long short-term memory-based networks. So there are those, and then DNN optimization and regularization, which are some ideas of how to tweak deep neural networks and so on, and improve their performance. And finally, some auto machine learning approaches, which are sort of used in deep learning architecture to make them do certain things really quickly or learn by their own. Okay, so these are the things that we'll cover in Fractal 1, and it's going to be an exciting few lectures. I am excited to teach this course. And in terms of evaluation, we'll have for the entire course, this is the evaluation. So we'll have two quizzes, quiz 1 and quiz 2, and assignments 1 and 2, which will be 30%. So one of the quizzes and one assignment will be from Fractal 1, the rest will be from 2 and 3. Okay. And then you'll have minor and major exams, which will be 30%, and the major exam will be 40%. So since this time we just have one minor, the minor exam, most of the portions will be from Fractal 1. So what we are going to deal with till like September or something like that. Okay. And in terms of reference text, we have our trusty old Goodfellow and Bengio's book on deep learning. So this is sort of like the base with which there'll be a lot of stuff. Although in my lectures, I've picked my resources from several different areas. So the lectures are important. It's not just following the book, but the book is a good sort of place to kind of get the basics down. And there is obviously introduction to deep learning by Charniak, but I'll point you to specific videos and articles in class, right? So always I'll have a link in the bottom of my slides about where I took certain information from. So you can go and look at the source information and you'll get to know a little bit more about that slide. Sounds good? Okay. And class timings are this. We will discuss the Saturday aspect at the end, but Sunday we are meeting from 9:45 a.m. to 11:15. All right. And finally, let's start. Okay, deep learning. And let's talk about the aspect of deep learning from the point of view of why did it emerge in the first place, right? What was the idea behind deep learning, and where these fields got merged between, say, artificial intelligence, machine learning, and so on, to give rise to such a interesting area of both application and research. Now, if you look at artificial intelligence, it's like this whole universe, right? You're trying to kind of understand how to enable computers to mimic human intelligence. That is, you're trying to come up with interesting ways to see if humans can perform certain tasks that humans perform so seamlessly, right? For example, can you give me one example that humans perform seamlessly that computers struggle with, or at least seem to struggle with? Anybody?
Recognizing face.
Image
Yeah.
recognition.
Image recognition, absolutely. That's one of them. Anything else?
Reading
Speech
writer.
recognition.
Yeah, that's a good one. Anything else that you can come up?
Sentiments.
Hmm?
Sentiments.
Sorry, come again. I didn't hear you properly.
Sentiments.
Sentiments, yeah, emotions, right? Yeah, perfect.
Yeah.
Sounds good. So these are all like certain cues that we are getting. And in fact, that last example is very interesting because I am a neuroscientist by training, right? And I am interested in understanding human emotions. And sometimes you can see that even humans struggle at picking cues, but there are a lot of these factors that come into play in order to understand what's the emotional state of a person, where there are some certain challenges to understand what are the features involved. So that's a good example, right? So we have all these scenarios where artificial intelligence is this way to kind of bridge between what humans can do and can we make computers do them, right? Now if you look at within a subset of this is this idea of machine learning, right? The concept that is it possible to learn something without me explicitly saying that this is what you want to learn or this is what you want to do, right? Or explicit programming, can we understand, is it possible to do certain recognition problems? So you said image recognition is one of them, right? Like we are really good at it because we have a nice library of resources which says what is what, right? And we use our information from our senses in order to place information into certain categories, right? And obviously I don't think there are a set of rules that says that, oh, if there are two eyes, one nose, one mouth, two ears, and this particular orientation configuration, that's a human face, right? But that sort of evolves naturally. And in some sense machine learning is this idea that you are giving machines the capability of learning certain things without explicitly saying the set of rules, right? So that's the idea. And then there are many sort of forms of this, which is not the scope of this particular class, but a machine learning course, which is, I think you might have done it in the previous semesters, would give you some idea. But what we are interested is probably a subset between both, right? Like the idea of deep learning, right? And when you say deep learning, which I'll come to in a slide or two, the real sort of reason why the name deep learning came into the first place, right? That you are trying to extract certain patterns from the data, right? Certain patterns that probably you, with immense amount of training yourself, would be able to understand to some extent. That is something that you're trying to teach it or make a machine learn, right? And the fact that you are trying to do this with specific architectures, right? And whenever you look at deep learning, it's all the idea of this specific architectures. In fact, the entire space of artificial neural networks, which grew as a separate section of connectionism and psychology, because the artificial neural networks was not born in computer science. In fact, it was born out of understanding how the brain works and so on. And there was a very good a psychological component to it, because this whole idea of connectionism, right? Or um, uh, what's often called parallel computing processes, and these are sort of the roots in which these deep learning architectures were actually taking rudimentary shape at that time in the 1980s and so on, right? And in fact, how do we extract these features and patterns from the data, right? And do it in a way that's there without explicit programming, with the aim of enabling computers to mimic human intelligence, is this idea of deep learning, right? So there is this layer in which this sits, which is having a specific goal. And in fact, when you look at many of the literature and initial literature on deep learning, it's often referred to as representational learning. Yeah. Any idea why the name representational learning? Can anyone sort of give a reason or probably think about this? Why should it be called representational learning?
Because suppose if we are giving a pixel size of photo of cat or dog,
Yeah,
so
yeah.
it doesn't that it is a cat or dog.
Mm-hmm. So what is it doing there? As in, what is the idea of representations in the first place?
Okay, the idea of representation, it seems that, okay, suppose if it is an animal, it is an animal, if it is a human,
Mm-hmm.
it is a human, and then based upon the person detection or the human detection or the animal detection,
Yeah,
then decide that this is a cat, dog, or a
yeah, yeah.
female.
Cool. Yeah. So that's more or less the point, right? The representational learning is it possible to build certain underlying, so it's not just features, it's certain combinations of features that give rise to certain certain higher level constructs, right? Or higher level representations which help us make certain decisions, certain solve certain problems, and in fact these sorts of architectures give rise to a very nice hierarchical representational organization, which was the foundations of deep learning, right? So as the example was said, in understanding a cat is a cat and a human is a human does not only depend upon the pixel level information, but there is something higher level to it, is the idea. Okay. And please feel free to interrupt me anytime if you have a question. Yeah, I'm happy to have this as more as an interactive session. And then shout it out. Don't write it in the chat because I can't look at it. Okay, so why did deep learning emerge, right? Some of the questions that we asked in the previous slide sort of makes this question relevant, right? Anybody care to give a go? Why did deep learning emerge?
Because sir, we have more data, and right now we had more compute power also.
But that's more of a, you mean to say that, oh, we have more data, so that's why deep learning emerged is not probably the right direction.
Sir, I
So,
think because of the limitation of the machine learnings, because it was limited to linear patterns.
That's a very good point. Yes. But uh, why? So
yeah,
that's still mathematical. What's the intuition? What's the intuition behind it?
So
we are
the
trying
human
to,
brain functions,
Some,
the
some
urge,
one at a time. Yeah.
yeah,
Sorry.
yeah.
Yeah.
So mimic, sorry, yeah, Sudeep, go ahead. Yeah, so the urge to mimic the human brain, exactly.
Uh,
His
uh,
answer. Same.
totally. That's the answer. But what I'm trying to say is, it's a slightly sort of come a little bit one level lower than that. Okay.
we are trying to go closer prediction.
Okay. Anyone
Sir,
else?
the intuition behind deep learning is actually it rooted in the desire to mimic the hierarchical learning processes of the human brain. Okay, for
Sounds good.
example, to automate this feature extraction and to leverage
Absolutely.
the guarantees of this
Cool.
automation,
Yeah.
handle complex pattern recognition, etc.
Absolutely. So that makes a lot of sense then. Okay. So to put to you in a very simple word in that, typically features that are hand engineered in sense that you look at a person and you start saying that if the nose is 0.5 centimeters away from the lips and if the eyes are 10 centimeters away from each other and so on and so forth, so you're sort of doing all these things, and then it is a human face. If you kind of make those sorts of understanding, these are not scalable, right? The minute a face changes slightly, or if there are certain perturbations, your method fails, right? Typically. So let's look at some of the ideas, right? Like there are, if you give, let's take an image example, which people often are, it's easy to contextualize it. Then you have lower level features like images have edges in them, images have borders, images have contrasts, for instance. And then if there is a specific information in the image about certain mid-level features, for example, let me take an image of a face, right? The face, there's an eye, there's a nose, there are eyebrows, there is mouth, and all that stuff at such specific, relationships to each other, right? And obviously there are high level features, right? Like how the face is the face of a man or a woman, and so on and so forth, right? Now, if you imagine that you had to hand code all these features, right? Be a nightmare, right? Like you have to probably imagine doing this for each and every one of them. And that's how artificial intelligence actually evolved, right? Now, because we take this for granted that this is how things are done, imagine in the 70s when people were writing a set of rules in AI. That's how AI was developed. It was a set of rules that you had to follow in order to kind of get one task done, right? But people realize that this is not scalable. Anything that's new, anything that comes from some new information or new data completely will break it, right? And but in case of humans who are really good at computer vision problems, right, recognizing images, they do this seamlessly, right? And that means that there are certain sets of features or certain sets of architectures that are amenable to change in such a way that extracts certain generalized features from, say, an image or whatever it is, right? So that's number one, right? That hand engineered features are not scalable in some sense. Second thing, they're very brittle. Okay, so let me give you another example from this paper, right? So the idea was to actually extract information about two different things in this particular let's say, oh, I should not have shown you this, I'm sorry. Damn. Okay. But anyways, that spoils it a bit. But if you give these two things as template to an image like this where there's a lot of clutter, right, and you have to find out, right? Now what do you do here, right? You do a search, right, a visual search, and you find out where and all this particular thing matches the template, right? Now, in fact, in this case, you can see the object here, but it's in a very different orientation compared to here, right? And you can see this, the frog is here, but then it is occluded by another thing here, right? Now, the problem is that you could do this in a hand wavy thing, right? Like this paper exactly does that, right? It tries to identify certain relationships in this feature that will fit, and then does certain ways in which it can rotate the image, scale the image, and then find out these areas, right, where you can see the images and compare them. But if the same thing is used in different locations, different lightings, different observations, then it breaks, right? So they're very brittle. So the point of deep learning was, is it possible to automate this in some way, or is it possible to extract features that are not just a function of our intuition about how the world works, but from the data itself? Does the data give us enough information to extract these things? That was the idea. Okay, so that was one of the initial thoughts that they had when deep learning started emerging, or at least started building up. Okay. Now, when you look at the history of deep learning, because it's important to know where you came from to know where you are now, always, right? Now, if this is a timeline from the 1940s, you can see that there are three distinct bumps here, right? These bumps are corresponding to certain relevance of ideas in artificial intelligence, which then later actually realized into deep learning and this field that it's rapidly evolving right now, right? The idea came from cybernetics initially in the 50s and 60s, right? Followed by what I called as connectionism, right? Like these ideas of parallel computing networks, which mimic probably what the brain is doing. And it was highly studied in psychology. In fact, to tell you a story, I did my postdoc in UCSD, which was one of the birthplaces of the connectionist, connectionist based models. In fact, if you know perceptron and the backpropagation algorithm that was developed by Frank Rosenblatt, it happened in one of the psychology departments which I was in at that time, and then they gave us the history about how that happened, right? Like where they thought about this idea and tried to develop it. So it was fascinating to see the initial underpinnings of what is now a very rapidly emerging field. And right now it has evolved into deep learning, but there are other certain minor things here that we need to understand, right? When initially when things were happening, computers were being becoming a little bit more powerful and doing things, in fact, the classic algorithm which has been used, which is used in deep learning, which is also something that we're going to look at, the idea of gradient descent, has been there from the 50s, right? The idea that you can use, the gradient of a function to perform function optimization has been there from 50s, right? Right. It's just later that they thought of applying this to certain specific architectures, which completely opened up a lot of possibilities. Right. 1960s is where a perceptron came into this thing. We look at what a perceptron is, but these are simple feed-forward neural networks with just a single layer. And then the backpropagation algorithm sometime in the 1980s, right? And in fact, I heard a talk from Don Norman, who was the advisor of Geoffrey Hinton, Frank Rosenblatt, and all those guys, right? So very fascinating to hear the history of this. But then came actually these deep convolutional networks in 95, right? The initial paper in 95 that came, and then things have never looked back since, right? Like we have this big boom right now. And since it's a very rapidly evolving field, it is often good to be updated about it because it's changing, and there is a reason why it's changing rapidly, because it's a very nascent thing. And so people who are interested in this should keep yourselves updated in what is going on as well. Okay. So, and obviously, as someone pointed out, there's big data. Now there's superb hardware out there which can do like magical things. And obviously we have open source toolboxes, which one of them which you'll use for your class in your assignment, for example, be it PyTorch, TensorFlow, and all that stuff, which is open source, which helps us build these neural network models and realize deep learning's power, right? So all these are combinations of why we are here at this particular point. Okay. Sound
So,
good? Yeah.
one
Yeah.
question.
Mm-hmm.
So, did we just move to deep learning because it was better, or there was some like serious limitation to machine learning? Like,
Exactly,
let's
right?
say,
Like,
I mean, my question was like, even like linear regression has we stick to linear boundaries, but there are other algorithms like SVM which can do,
yeah,
difficult boundaries.
yeah,
So like,
yeah.
why didn't we like expand more into like algorithms which can learn difficult boundaries rather than moving to deep learning? Like, what
Sounds
was the thought process?
amazing question. Yeah, that's a really good question. So, I guess there are two things to it. I wouldn't say we stopped, right? We did not stop. Still, there's work going on in all those other areas of machine learning as well. But what we realized was, if I do that for every single type of boundary, for example, let's take for instance, right? Let me show you an example. Let's take a case where there's two features, x1 and x2, and then there is some belonging to a class here, and then another belonging to a different class in this outer loop. So let's say this is class 1 and this is class 2, right? Let's say, for instance, right? Now this problem can be solved in a few ways, right? And first thing is, are these classes linearly separable in this dimension?
No, linearly
right?
not separable.
Not
It is not separable.
Yeah. So give me one idea of how you can separate them.
Features can be transformed, then logistic you can apply
We
Excel.
can increase the
What sort of,
dimensionality.
absolutely, what sort of transformation would you use?
Turn it into a cone.
Sorry.
Turn it into a cone.
Beautiful. So that means that you are adding a dimension, right?
Yeah, we can
Yes.
increase the dimensionality.
So you're increasing the dimensionality. So in some sense, but there's another possible way of doing that, is at this level use a kernel which is Gaussian in nature, instead of using a kernel which is so everything is kernel in some sense, right? Even a straight line can be thought of as a kernel. Instead of using a straight line as a kernel, if you use a Gaussian kernel, you're sort of separating the ones, and you can use the threshold of the standard deviation of this Gaussian kernel. Or you, in another words, it's interpreted as you can increase the dimensionality so that you can separate these two out with height, and you can then insert or make it linearly separable. There is another way of doing this, would be to do what's called a polar transformation, which we'll look at, which will make them linearly separable again, right? Because the radius are very different of this and these sets of points, right, that are within the annulus. So
why don't we use like an area of circle kind of equation?
Yeah, that's what I'm saying. The polar transformation here does that. What my point is, now you came up
So
with
how it
such.
works? Polar transformation, how it works?
So you go from xy to r theta. I'll show you this example, same example in a couple of slides. But you go from xy coordinate, so this is xy, right, to r and theta. Okay, so that will separate it out.
Okay.
Okay.
So your
So-
plane will become separated like that?
Yeah, you can do that. But what my point is, I'll tell my point here so that you get it. Did you see how many methods you use to get to the same thing, right? Yeah. Now imagine I have just one way, one sort of way to do this problem, and the minute I change the characteristics of the input, the same network is possibly able to do the same thing. So the idea of scalability and generalizability is why deep learning emerged. Okay, there are two things for that. That this problem requires a specific type of kernel, and I can give you a different type of a problem where the boundaries aren't well defined. Yeah, and still the same network with certain tuning will be able to learn this. So you do not have to come up with a certain different method and come up with some ingenious solution to solve this, because the network has inherent properties that will be able to do this exact thing, for example, right? So the ultimate aim then becomes that you can now pretty much have how much data ever you want. If you have a network that's able to solve a specific type of problem, then it can be generalized to problems in that entire domain, and that's why deep learning emerged, right? So does that answer your question? So that is the reason why this happened. That does not mean that you can come up with very interesting ways to solve a problem which has very nonlinear boundaries or different types of boundaries, but there's a much easier way to do that, right? I would say, I would put easy in quotes, or a scalable way to do it, and that's why deep learning came into existence.
So, sir, would it be right to say that we can employ some other machine learning techniques if if we know the domain of the problem and what exactly we are trying to solve?
Of course,
If it's
of
a
course.
very-
Yeah, in fact, that sometimes works a little bit better. But what people have seen is that the just by adding to those initial few simple architectures, that is making them a little bit more complex, seems to solve your problem. Although you are there is a problem of explainability there, which will come later late in the course. But the idea is that just by adding more and more layers to a network seems to solve your problem. Then you start relying on the machine to do its work. You do not do the brunt work, right? You don't and especially in areas of problems which are very hard, like for example language, right? Yeah, I mean, okay, has anyone come up with a sort of a comprehensive theory for language which can probably explain the nonlinearities, the redundancies, the thing? Whereas you have a deep learning network that can produce seamless language that will make you even or trick you in some scenarios, human like speech, right? Which is a tricky problem. Now, problems at that scale, you cannot think of hand made engineered solutions, right? And there are probably certain problems where, or a subset of problems where that will work, but these are the scenarios where this would have a edge, and that's why it works, or it's evolved. All right. Okay, so with that history, let's dive in and then look at some of the different types of computational problems that we are typically tackling in sort of both in research wise and also sort of real world applications, and then see, maybe there are how we can take the deep learning approach to kind of connect these problems to using those sorts of methods. So often problems are either supervised in some sense, that you guys all know what supervised learning is, and the idea of teaching a network what to do, what's right, what's wrong. And obviously these are the initial steps, right? Like regression, classification, regression or the prediction problem, or you're trying to classify between different classes, often recognition problem, right? Or what's called a discriminatory problem. There are areas of computer vision, right, which is often a computational problem of understanding images, recognizing them, recognizing parts of the image, explaining what the image is, right? And even sometimes predicting from the image what happens next, which takes us to time series analysis, right? Like you have series of information that goes across time, right? And then the aim is to start predicting what happens in the future, right? So these are again problems that are in some sense supervised, because you have previous data to kind of teach what's going to happen. And then comes unsupervised problems, right? Like for example, feature detection, right? You are trying to identify features which have to do with certain aspects of what the image is about, right? You are learning from the image itself. And things like recommendation systems, you might have seen this, right? Like what Amazon, Google, Netflix do, right? From your pattern of activity, kind to find out what best suits your, flavor of content. Now, all these sorts of problems you can see, right, have in, if you can imagine, or if you had some, previous understanding of what deep learning is, and you've seen some videos and so on, there are all these problems currently have a deep learning equivalent for them, right? Now you have feed forward neural networks here. Typically, they do a really good job in doing this. And for computer vision, you have what deep networks? CNNs, yes, convolutional networks, or sometimes called DCNNs, deep convolutional networks. Time series analysis.
RNN.
Yeah, the current neural
LSTM.
networks. Yep. So LSTMs are a subset of RNNs.
GRU. Yeah.
Yeah, GRUs. Yes, GRUs are also GRUs, LSTMs. Yep. And what about the unsupervised part?
PC. Like feature
Sorry,
detection.
come again. Sorry, I did not hear you.
Principal component analysis.
So that's a method, right? But what sort of networks do you think can do this?
K-means.
No.
Graph neural network.
Yeah, very good. Graph neural networks, deep graph neural networks. Good. What else?
K-means clustering.
Those are machine learning methods, right? Those are slightly more shallow, which we'll come to. We'll look at shallow versus deep, but but what sort of networks have you seen? Have you heard about things called autoencoders?
Yeah.
Autoencoders, deep autoencoders. Yeah. Recommendation systems. Think about that. Same thing would apply.
Probabilistic models.
Yeah. Have you heard about GANs, generative associative networks? Yeah. So all these sorts of networks can generate new information from existing data, right? Sort of generate more data for a particular network to learn further, right? Like if this is your pattern of activity, what likely could be the future part? And in fact, in that sense, GANs can even be used in time series analysis. But there are combinations and so on. But you can see that how each of these problems have a very specific architecture that sort of solves this, right? Like, and you can see why they evolved a little bit later in the way that they did. But already you can start seeing why these things emerge and why they are important, because these problems are very important in real world applications. Okay.
One question, sir. How computer vision comes under supervised?
It's still in the sense that you are trying to extract features and the ultimate aim is to recognize stuff, right? So you need to have that ability to know what is what in order to recognize that. So that's why. So, I mean, I would say part of it is supervised. It's not entirely supervised, but I just want to kind of place it there. Yeah.
And where, sir, NLP or Gen AI comes unsupervised or supervised?
That's a good point. NLPs are more sort of combinations of each of these things. It can't be placed in, and I thought about that, where to place those, but for the sake of be keeping it very simple, I just did this. But there's a lot of combinations of, you can think about language as a time series data too, right? In some sense that it's a linear sort of information that flows across time, and you're trying to predict the next word or the word based on the context, right, or history. So you can think about RNNs are a good model of even language, right? But right now the transformer models just blow them out of the window, right? RNNs are now what ancient dinosaurs compared to transformer models. Okay, sounds good. All right. So now let's come to this idea of deep versus shallow learning, guys. Now I'll put this question to you. Oh, what is deep? What is so deep about deep learning? Why is the word deep? Hey, have you ever thought about that? Right? We say deep learning. Why
Number
deep?
of layers.
In depth.
Yeah.
Right?
Lots of layer we are using.
So that's obviously always the answer. In fact, that's not the complete answer. So if in an interview somewhere people ask you, oh, why is it called deep learning? And if you say the number of layers, that they'll not accept that as a complete answer. In fact, think about it a little bit more.
You
Sir,
try
deep
to
learning, we are trying to
add
find out
learning
the
on the.
structure.
Sorry, guys, one at a time. Anyone, go for it.
You try to learn on the previous learning, and always refine that learning by adding more layers to it. That's why it's
Sounds
called
good.
deep.
Sounds good. Closer to the answer. Next, the other person.
So deep learning, we are trying to learn the structure of a system, and machine learning or shallow learning, we are trying to go by a vector or by some feature. We are trying to divide the system.
Right. But why the word deep? The answer was
We are
closer
trying
to the
to
person previous.
The deep hierarchy of
Good. Hierarchy. The words are coming out. Yes.
hierarchy of layers, basically.
Right. Why is it a hierarchy? Have you thought about the word? Why hierarchy?
So I think
What does hierarchy mean?
we are trying to find out more complex patterns from the data. That's why.
Yeah, from simpler stuff. Very good. Right. So the deep does not refer to the fact that it has more layers, right?
So
The deep refers.
like a recursive
Mhm.
process, right?
Right.
That is where we have the deep coming from. Like we have number of epochs, and then based on that we have more.
No, that depends on the data, right? So the epochs or the recursive nature is you're presenting it more data, but the deep aspect is more to do with the hierarchy. The hierarchical word is correct. But what we're trying to do there is, as people pointed out, is we're trying to learn from simple features, but we're building on the simple features, right? Now, in the future, there could be models where the extraction of deep features from a particular image or very complex features can happen in a few layers too, right? You don't know that. So it's not just the layers that give rise to what is called deep learning. It happens so that having many layers gives rise to more complex representations of the input. But the deep word comes from the fact that you're trying to build much more informative representations, complex representations from simple ones. Okay, so you're trying to divide and conquer the problem first, but then when you divide the problem, you're trying to then build upon those small bits something much more concrete and much more whole, right? So when people ask you deep versus shallow, it is this hierarchical nature of deep learning that gives rise to the word deep, right? So let's take an example, right? Let's contextualize this. Okay, so one idea is what we discussed before, right? Like the idea of linear separability, right? One of the points is that at certain level, right, things that are not linearly separable. For example, the same thing that I gave you here, you have a certain set of class problems which say this belongs to class 1 and this to class 2, right? So if you have such a data, then you can imagine that at this particular level of hierarchy, this is not separable by a simple linear line. But if you have to separate this just by a line or a plane, for example, now you have to transform this data, right? Let's say you want to transform this data but still keep the dimensionality the same, right? How would you do this?
Polar.
Cool. Yeah, that's what I was talking about a little bit. So if you do a polar transformation, this is what you get. Right. So the same points in the same dimension can split into two things, right? Now, what I have is at that same level, right? At that same level, a different transformation of the data that gives rise to a scenario where this data is now linearly separable, right? Now imagine, right, like if I could do this with a network and it becomes much more complex than this, and I start learning much more deeper relationships among the data, right? Right. When this is, so that's the thing, you are learning deep relationships. You are not learning, or you're not deep because you have increased number of layers. You are deep because you learn deep relationships about the data, right? You are learning the fact that there are ways in which the data is distributed, that upon certain ways of looking at the data can come out very clearly, right, at certain level of depth. And that's the idea. So let's take a real world thing. Let's take this image recognition example and let's make it more concrete. So this is a Samoyed and a wolf, guys. Okay, the Samoyed is a breed of dog. This is a white wolf, right? They look similar, right, in some sense. But if I give you these two pictures, you would be able to recognize both. So let's take situation number 1. Situation number 1 is this. There are two Samoyeds, different orientation, different lighting. So they are in different orientation, different lighting, right? Now, if I show you these two pictures, what would you say? They look similar, right? Yeah. Now, if I take what's called shallow features, as in the features that probably are not informative about the whole image, but just tell you about certain properties of the image at the most lowest levels. Let's take something like pixel level information. If I just take this to understand about the image, are these similar or are they different?
Different.
They're different.
Different.
Right? Yeah, they're very different. So you can clearly see that, right? And I'm taking information from pretty much the same area that corresponds to the forehead of the Samoyed, right? So what this become, right? This becomes a scenario where shallow level features are not able to do the same thing, right? Like, or are not able to distinguish between, or it's distinguishing between two images which belong to the same thing. Yeah. So solving a problem like this now requires us to understand that, oh, this is the same thing but in a different lighting, right? Now imagine that as a computational problem. It's the same thing in a different lighting. It's very easy to say that, but it's hard to compute something like this, right? Like if you had to extract out what it means to be a Samoyed like features, right? That requires something much more deeper than the pixel level features, right? So that's where the word deep comes from. Okay, now let's take another situation, same thing, but this time a wolf and a Samoyed in similar environments, right? They are pretty much in a forest where the sun is shining on them, and then I take these two, and what do you see between them? Are they similar in some sense?
Yeah, more similar.
More similar, like similar-ish, right? But if you take the whole level features here, you would be able to say that this is a wolf, that's a Samoyed, although slightly difficult here. But there are features here that can help you do that. Now, this is what deep learning helps you achieve, right? This hierarchical building of complex representation that can, at some level of depth, help you understand certain differences, right? And at that depth, this whole nonlinear composition of these two images, right, comes out to become a representation which then splits us and helps us understand that this is a wolf and that's a samoyed and not the same thing. Okay, got this? Any questions here? Okay. So that's the idea between deep and shallow learning, and the reason why we are doing this in order to understand certain problems at a much higher level of hierarchy where things are more interpretable in terms of this large scale context.
So, sir, are we saying that we just have pixel level data? Then
I mean, I'm just giving you an example of pixel level data as a thing. I can give you even further features that are probably very similar, right? Probably the snout and the area around the snout of those things are very similar too, right? And those are still complex representations, but at that level, still they could not be separated out. Now you might have to take into their eyes and the entire thing as a whole, right? So now what you're doing is you're trying to build more and more complex representations from these simple building blocks. I'm giving you pixel level information as an example to kind of illustrate the fact that what is shallow about the learning and what is deep about it. Okay.
sir, are we saying that is it because of the lack of the features that we have, then it becomes a shallow learning, whereas when we have more features, like not more, but features
Yeah,
that give different data.
exactly. So that's where in your own sentence, can you see when you said more, it's not more. What is it?
It's like features that give different information, like of different aspect of the.
Exactly. So how do you build in features that you give you different information?
Like,
How do you do
as
that?
in,
Yeah.
like collecting different data and then manually.
Right. So can you see that the idea is not about having more features? Okay, the idea is about having complex features, as in there is a way in which features combine with each other, right? It's what's often called in neuroscience a binding problem. You're trying to take the individual sensory aspects and bind them to give you a proper percept. In that same sense, you are trying to combine and bind features, okay, which will be it the fur color, the snout shape, the snout color, the eye shape, and so on and so forth, right? I'm just giving you some examples, but how they combine with each other is what the deepness aspect captures, right? And the deep part then becomes synonymous to the fact that when you add more and more layers, you get deeper and deeper representations of the image.
Okay, got it.
Okay, cool. All right, so with that, let's move on, and first let's start talking about a simple feed-forward neural network, right? Like we got to start somewhere, right? In the deep learning part, we kind of know that deep learning is all about having these artificial neural networks and sort of having very specific architectures to solve specific type of problems. And the basic comes from the fact that we have a simple feed-forward neural network called perceptron. Many people must have have seen a video or have a look at some books where people people have seen this, but let's just look at it because this is the building block, right? We got to look at that. Now, a neural network is nothing but something that's taking in a series of inputs. And the idea that it is a neural network was inspired from the neurons in the brain, although it is not what the brain does. Okay. Yeah. So in the brain, a neuron basically takes information from other neurons via what are called dendrites. And then they sum up at the cell body, often called the soma, and the neuron fires because of that. Okay. when I say neuron fires, it generates what's called an action potential, which is a spike. Okay. Taking inspiration from that, a neural network is nothing but something that takes in a series of inputs, right? The series of inputs can be anything, right? Here, this can be series of features. In the case of an image, it's a series of the pixel information, right? Or anything for that matter, right? This is the series of inputs. They combine with each other and they're often weighted. Now, the neural equivalent of this is that whenever a neuron receives information via its dendrites, the dendrites can increase or amplify the amount of information coming in or suppress the amount of information coming in based upon the type of chemical present at that level. So you can imagine that to weight the information, that is, if this is high, then is sort of like a gate that's allowing information from X1 to kind of dominate and so on and so forth. And then they sum up, okay, at the level of the body of the cells. In this case, there's a unit that sums everything up, a weighted summation. And then there is a nonlinear transformation in the sense that there is a all or nothing response. So for example, when a neuron gets information, right, from everything, it generates a spike, right? A spike lasts for around 1 millisecond or so, right? It's like a spike, and that spike travels along that zone. So that's how a neuron does it. But taking inspiration from that whenever things sum up and they cross a certain threshold, right, then the information either becomes high. If it does not cross the threshold, the information stays low, right? And that's giving you your output. All right. Now, mathematically, you can write this as something like that. Right? So your output y is a summation over I, 1 is to m inputs, right? Wi xi, that is, we're taking w1 x1 plus w2 x2 plus dot wm xm, right? And then after summing all these things up, you are passing it through a nonlinear function, right? And this nonlinear function, we'll discuss, there are many types of nonlinear functions that we can use. What is it called in the neural network literature? Anybody knows what this is called?
Activation function.
Cool. It's called an activation function. Why the word activation?
You are adding non-linearity to the linear function. So
Fine, but
that's
why
the
is it called
activation.
activation?
Defines the output of that layer.
No, that's true, but why activation?
Because of the threshold kind of, it
That's
like
great.
acts.
That's very good. That's very good. That's the reason why. The thresholding nature, because it is activating something or not, right? So in some sense, it's all or nothing, but that depends on the nonlinearity, right? In this case, what I've shown you is what's called a sigmoidal nonlinearity. That is, you have a nonlinearity in some sense that above a certain limit, the output turns to 1, otherwise it stays 0 for certain values of x. Okay, so the activation part comes from the fact that, if it crosses beyond a specific threshold, it activates the neuron, right? So that's the reason why it's called an activation function and not anything else. Okay,
So like, what is like W in the case of human brain?
that's a good point. In the human brain, right? So there are other neurons. In fact, let's say there's another neuron that comes and what's often called a synapse, right? They synapse onto this, right? At this synapse, in fact, the amount of chemicals, it's often, those chemicals are called neurotransmitters. I'm just going to put NTs. Okay, the neurotransmitters decide whether a current information that's coming to this particular dendrite is going to activate and send information, or is it going to suppress, right? So in some sense, that's like a positive weight or a negative weight, right? So it's either scaling up the input or scaling it down in some. Okay, so or changing its sign. So that is what is the equivalent in the human brain, although it's not exactly the same way. But this is a good abstraction of this particular process. All right.
So for the activation, you are saying that after a given threshold, it will be activated or it will be suppressed, right?
In sense, if you depends on the strength of the non-linearity, right? Like if I have like a step function, okay, right, which is 0 and then 1, right? This is a step function, right? Now this is a very what's called a hard non-linearity.
This means activation means including that, like that.
Yeah. So in sense that if the x crosses a certain value, right, then that particular neuron or w times x, I wouldn't say x. I should not call this x because it's a function of this. So let me call this entire thing to be x. Let's say, right? So this entire thing has to cross a specific threshold, and that will give rise to a higher activation of that neuron. Okay.
So every activation function will give some kind of what you call it as activation or but there can be functions which are linear like ReLU.
Absolutely, they are still linear in they are you should be very careful in the wording. They are not linear, they are piecewise linear. Okay, when I say they're piecewise linear, so the discussion here is about another type of activation function called a linear rectified unit. Okay, so or also called ReLU. Okay, so that means that the function is f of x is x for is 1 wait, let me erase this part.
X
For x greater than 0, right, and it's 0 for x less than or equal to 0. Okay, so that's a ReLU. So you see that is till x equals 0, it's 0, and then it becomes that, right? So that's the relationship between x and y equals f of x, right? So in this case, it's what's called piecewise linear. Okay, so that means that there is still some non-linearity in that in the case that if x is going to be less than 0 or equal to 0, the output stays small, right? But if it is greater than that, then the output scales with the input. That's a different matter, right? So there is still non-linearity here, but it's not as non-linear as I would say this is.
Sir, x
so activation
greater than
means
0, it is always linear, sir.
Sorry, come again.
Sir, actually, for x greater than 0, it is a linear, right?
Yeah, if for x greater than 0, it's linear.
So then how you can say it is an piecewise linear? It's always linear.
What is happening at x equals 0?
Generally, we use the term as piecewise linear for exponential curve. If you take exponential curve, then if you observe it piecewise, then we can say.
Fine. That's fine. But here, look at what's happening at x equals 0.
Shifting from 0 to some value.
So is it linear at x equals 0 or what? So for linearity, what sort of condition should be present? What is the mathematical condition for linearity?
Every x equal to y, like that.
No.
Should be some slope.
Fine. Or when I say when it is non-linear, what sort of test will you use to confirm non-linearity?
Means for every
everything is non-linear.
y will change differently, like that.
Yeah, exactly. So the point is that there has to be some discontinuity somewhere, right? In some case, there won't be a discontinuity. The function can change more smoothly, continuous as well. But at least in this case, the function is still continuous. It's non-linear because of the fact that above x equals 0, the change is different compared to when it's below 0, right? Or less than or equal to 0. So in that way, the function is still non-linear, although it is still continuous in some sense. At this point, there is an inflection, right? Now, for example, here this is a hard non-linearity. Here there's a discontinuity at x equal to 0, right? Whereas in this case and in this case, the functions are continuous, but the point is that there is a response is not as graded with x. When x becomes less than 0, the response completely changes, and that's the nonlinearity. Okay. All
Sir,
right.
the question I was trying to ask is, it gets activation means you are saying that just like neurons at synapse, it's either get activated, which means it gets increased or it gets suppressed, correct?
Right.
But in the ReLU, if you would say, after a point, which is x greater than 0, of course, it's continuously getting activated to some.
Sounds good. Yeah.
So it's not, I mean, it's said that for x less than 0, it's
in
getting
sense, it's
suppressed.
activation here, which is graded with respect to the input, but it's still getting activated. The level changes based upon the input. So that's still fine. But for x less than 0, it does not, right? So there is some way in which you introduce some nonlinearity in the response, right? So that's the point. Okay.
So either the activation should be of the nature that it should either increase or it should just suppress it. It should be the definition of activation.
In sense that that's why it's called an activation function. There is some activation beyond a certain threshold, but how does that activation change across time depends on you, depends on the type of problem you're trying to solve.
And activation also means that it can be suppressed also.
That's what these means, right?
I
Like
mean,
in sense,
with suppression, I mean negatively it can increase, right?
Yeah. There are even certain types of sigmoid function called tanh.
Yes.
Tanh functions, right? So which go like that, right? So it's +1 and then it's -1. So it can still suppress.
Okay.
Yeah. But the nonlinearity is above a certain point, it just stays static, right? The information does not gradedly change with the input, right? The information stays static with respect to the input. And at certain point, it again in the positive side. So these again are types of activation functions that can, go the other way, the other direction.
Do we have any limitation on activation function, or it's a state of art?
That's a good point. I think we'll come to that a little bit later. I'll tell you all about that. But to kind of quickly answer your question, the point is that the activation functions have evolved across time, and people have looked at things that work really well for the underlying problem. And sometimes that is why this is also an area of high research, is that what sort of activation functions can best fit. In fact, the ReLU function seems to be a really good activation function for a lot of intents and purposes. The reason being that it has this nice linearity that's above 0 that helps us solve certain mathematical problems easily. And as you say, someone pointed out, right, you can sort of approximate several functions using some piecewise linear functions too, right? And that way, you can make some certain complex shapes at certain levels of hierarchy, and that will give rise to nice complicated nonlinear boundaries that you can have. So but there are advantages in using other types of activation functions too. For example, sigmoid, right, that can be used for instance very good in classification problems, or when you're trying to do probabilistic outcome prediction, right? So probability of a given image X, right? So when making a probabilistic inference, having a sigmoid as an output which thresholds as 1 can approximate any sort of probability distribution, right? And that way you have a better hold on the problem compared to a ReLU function. Got it?
Okay.
All right, guys. So I'll just erase this slide, but I hope people were all on board with that. So as I mentioned, this is our nonlinear activation function. And sometimes, in fact, there is often a bias that's added to it. Now, do you know what a bias does to the activation function? Anybody? So let's take a sigmoidal activation function, for example, right? That is, a sigmoidal activation function has the y equals f of x is 1 over 1 plus e power minus lambda x. That's the formulation. If it has a sort of a slope, something like that, let's say, right? It goes to 1, and this is your y. Okay, so what would this bias term add, right? So because the equation now becomes something like this, right? Y equals sigma of wi xi plus b, and that's passed through the activation function. Now, when you add a bias term, what happens to this function?
Sir, you shift the
actually,
entire graph to a certain position wherever you want.
Absolutely, yeah. So you either do this, right? You either shift it this way, depending on the bias, or this way, right? So at the end of the day, what happens is you see the thing either shifted this way or shifted that way, right?
sir,
Now,
this
what does this do? What does this do?
sir, normally this shift allows the neuron to output a non-zero value even when all inputs are zero.
Absolutely, right? So it sort of shifts the sensitivity of the neuron, right? You can call it sensitivity, right? How sensitive it is to your inputs, right? Like, can a few number of inputs increase the activity of a neuron, which is what will happen in this case, right? When it shifts, or does the input have to cross a certain value that's much higher in order to kind of give that? Oh, wait, am I wrong? Yeah, the other way around, right? So in this case, there has to be an increased amount of input that should give rise to a value that's higher, whereas here even a small change in the input can give rise to the same thing. So that means that you're changing the sensitivity. That means you are sort of playing around with what combination of features can excite a neuron or not. So those are the ways in which a bias can affect the neurons.
But why do we need to do this? I mean, like, what's the benefit of having a bias? Like, I understand the point of moving it, but why do we need to move it?
Okay, so let's say, for instance, you did not have a bias. Okay, then what might happen is there are certain problems where let me give you an example, and in fact I'm going to discuss this example a little bit later. Can you hold on to that question? Sorry about that, because I think it will become much clearer a little bit later, right? I'll tell you exactly what it means, so just hold on to that question. But to answer you very briefly, there are certain problems which cannot be solved without a bias, and I'll give you very simple Boolean logic for why that won't happen. I'll tell you that. Okay. And B is the bias term. Okay. So what's the time now? It's around 11. Yeah, so we have 15 minutes more to go. So let's take a simple feed forward neural network, right? Like sort of a extension of the perceptron, right? And this is the case when you sort of extend the perceptron to form what's called, what you guys know what this is? If that was a simple perceptron, anybody has an idea what this is? Where you have what's called a hidden layer.
MLP?
Yeah, good. It's a multi-layer perceptron. What's called an MLP. Okay, so it has two inputs, two hidden layer neurons, and then one output, and there is a nonlinear transformation at each part. Okay. Now, these sorts of networks sort of evolved because people started noticing, right? There were problems that a simple perceptron could not solve. Okay, simple perceptron could solve problems where, let's say, at the two-dimensional situation, you have a cloud of points here and a cloud of points here, then it looked like you could pretty much draw a simple line across these two things to separate these out, right? As a classification problem, very simple. Now, in this context, a perceptron was doing very well. And in fact, there was a very scathing review in around 1980s where they completely disregarded this entire field of artificial neural networks because people were working with initially just perceptrons, because they saw that they came up with a very solid proof that these things cannot solve problems which are not linearly separable. Okay. And in fact, the people who are working on the field were highly disillusioned by this fact, right? And they were like, oh my God, now our entire careers are in jeopardy because this has happened. But then the realization came that the minute you add more layers, right, you can start solving problems that look like this at the input level, right? Let's say these are two different distribution of points, right? At this level, data is not linearly separable, right? That is, you cannot possibly draw a line through this which separates these two things out. Okay. And what they realize is that adding another layer in between can actually warp the input space. Right? Now, what you're doing is warping the input space in some sense, that you're sort of shrinking this into this corner here and sort of elaborating this. So you're sort of making the space stretch out such that at this level, things are separable linearly between, say, the red region and the blue region. Okay. So they came back to this realization that this is possible to do now. That means that by adding more and more layers, this nonlinearity can be projected into spaces where they become linear.
So is it in some sense like the kernel that we apply in SVM? Like
exactly, right? Like you can, that's what I'm trying to say. In this case, it's easy to do that, right? But as a problem for visualization, it's easy to do. But let's say, this was for an n-dimensional data which had a very complex distribution of data points, then you can't sort of make that. But obviously here SVM kernel would obviously separate these two things out. But a neural network can do the same thing as well. But now you see that what it is exactly doing, right? It's taking this space and sort of warping this space or distorting the space so that at this level, things become linearly separable. And so that in that sense, this is now a perceptron part, right? All you have done with this, with these two inputs here, is ensure that at this level, they become linearly separable. Right? So now you can imagine that you have a layer at a certain level of depth, right? There is a way in which you can distort the input space enough in order to make sure that things are separable at that particular stage. But it also is important to understand that what is the problem context at hand, right? It's not just that for a simple problem like this, you want to add more and more layers, right? At that point, nothing might be even happening, right? Things. But I hope you got the intuition behind why adding another layer sort of helps and what is actually doing it to the input. Right?
So, sir, when we say, I mean, like, are we reducing the dimensionality here, or like?
No, right? We aren't reducing the dimensionality. In fact, it is two-dimensional here. It stays two-dimensional. What is happening is we are warping the space. That is, something that looked like this at this level looks like this.
But how does like adding layers that do that? I mean, like
that's the cool part. That's the idea of the nonlinearity, right? That means that things are not scaling in the same way at every part of the input space. Okay, things are not scaling the same way. Things are scaling in slightly different ways in such a manner that if you can find out an optimum combination of the way in which you combine the inputs, you can come up with spaces that can become linearly separable. Right? Now, how this happens, I can show it to you. I'll show it to you with some simple scripts and all that. But I want you to get the root intuition of the problem, right? You want to warp this space. That is something that is curved here. You want to make that straight, right? Now, how will you do that? You have to kind of change how the input is being distributed, right? But in order to change how the input is being distributed, you need to change how the inputs are being combined, right? And that is what is being done at this particular layer.
So in terms of the diagram, just the representation part of it, the hidden layer 1 and 2 are just combined and shown there, right? One is
so for example, let's say this is x1, this is x2 at the input space, and let's say this output of this is, say, hidden layer 1 and hidden layer 2. What you are seeing here is h1 and h2. Okay, so for a given x1, x2, which is here, let's say, there'll be a corresponding h1, h2. So which will be different.
When we add two layers, the output of hidden layer 1, that becomes an input to hidden layer 2, right? Because
the output of hidden layer 1 okay, so you mean to say, I'm not saying this is not okay. Oh, sorry for the terminology. The hidden layer is just 1. There are 2 neurons in it. The input has 2 neurons in it. The output has 1 neuron. That's what this 2 means. So there is one hidden layer. So if there was another hidden layer, then there will be a combination of both the things going into it. So it's what's called a fully connected network, right? So everything is connected to everything.
Right. So should we translate? I mean, whatever you have mentioned, that if we add number of neurons, that is when the warping happens, right?
No. The fact that you make this transformation, that is, you go from your input space to a nonlinear transformation in the hidden space, is what's warping it, right? It's not even the fact that you're increasing the dimension here. For example, if I add one more neuron here, right? Let's say I add it here. Okay. So, and this again combines to this as well. Now what you have is H1, H2, H3. Now this becomes a 3-dimensional space. Right? So now this input gets warped into a 3-dimensional space, but it turns out you don't even need to go a higher dimension, right? For such an input, even you can stay in dimensions, but you just have to warp the space around in order to make sure that they become something.
Sir, one question.
Yeah.
Is that warp diagram is the final output, or is the hidden layer output?
It is the hidden layer output, right? So so you can imagine my previous example that I gave you here, right? This one, right? Now this one has at the input space, and then at the output you are trying to find out a way to separate them out. The same idea here, but at this level they are not separable by a line, so you transform them, but at this level they are, so you then take the output. So this part becomes like a final perceptron, and this will all make sense when you look at the CNNs, right? Because if you imagine, in the CNNs actually extract specific features in a specific architecture to a certain depth, but after that the layers become fully connected, right? And the reason why is that till that level you are extracting certain features, and then you are extracting much more you are trying to warp that final feature space in order to give rise to linearly separable components at the end.
Sir, one question. So, is it always possible to distort the input to make them linearly separable?
That's a very good question. Superb. Answer is no. I would say no. I would say why. There is a possibility that you might not be able to completely linearly separate things out at a specific depth. And that is the reason why specific architectures evolved in deep learning. right? Now, why wasn't the same architecture of a feed-forward neural network used for image recognition? Can anyone tell me why? I mean, if this was the same thing, right? If this was happening, and according to the statement that, oh, it is possible to distort the space, then why wasn't it used, right? Can anyone think of an answer?
The dimensions are very high for a picture.
Still, that's okay. We can handle the dimensionality.
Sir, could you please repeat the question?
The question is this, okay? Now we know for a fact later, right? Let's say we have hindsight now. The hindsight is that, oh, there are these special type of neural networks called convolutional neural networks, CNNs, that help in doing this image recognition problem very well, okay? Or image classification, image discrimination. But if I give that as input to a feed-forward neural network, from the question that is any space that is non-linearly separable at the input level be distorted to make it linearly separable? If that is the question, and if I say, okay, probably the answer is, okay, you could do it, then why isn't this same sort of architecture used for all the problems?
Because
No, because in that case, okay, yeah, go ahead, Chandramohan. I mean, yeah, one thing is that dimensionality is very high, that Bala told. The other thing is that there are CNN models consist on images, which consist of 3 types of primary layers. So at the same time, if you parallelly handle 3 parallel layers for a multiple hidden layer, it will work
I
in a
know.
better way.
No. So I'm asking a much more primitive question than that. I get your answer, but I guess the entire crux is hidden a little bit.
Because sir, suppose if it is
Yeah.
a image or if it is a video either 2 megapixel or 4 megapixel, then why we are using CNN or why CNN is best in image and video? Because we have to adopt the pooling layers and also.
No. That's the thing. That's what I'm trying to say.
Sir,
Why not this then?
this kind of
Yes.
warping that we just did, probably if we do this again and again, we might lose the actual feature.
Absolutely. That's the answer. Very good. So the point is that although it was possible that it's linearly separable, but does this solve the problem at hand? Is it actually going to separate out, say, whatever you want to at the end? Is it going to separate out a guitar image from a violin image, which kind of look very similar, right? Now I can say that by combining the input features or mixing everything with each other might still give rise to a distorted space that could be linearly separable. But does that help you separate the problem of image recognition of certain types of inputs? That you still do not know. Yeah. So this is an example, but the consequences are very profound, right? So everyone got that point? It's important to clearly understand that.
No, sir, I'm still confused. Like, what do you mean by, like, exactly?
One I'm trying to say that okay, let's take a two-dimensional example because it's easy to contextualize it. This space becomes warped into this space, okay, right? But your initial motivation was to actually take this space, right, and then classify this area as blue and this area as red, okay, and at this level that has happened, okay. But let's say there was a scenario where the blue space was not the space that you actually wanted to find out, okay, and let's say the blue space was also peppered into these red regions in some way. Let's take that as an example. Now even if you warp this space, although in this case it's separable because this is what you want to do, it might not so happen that that is the problem you're trying to solve, okay, right? So in sense that this sort of architecture might not be helpful in those scenarios, but there are other ways in which you can actually do it.
Sir, here can we scan through that whole thing and check where those peppered
Yeah.
blue images are there?
Yeah, peppered points are, but the issue is that if the space is huge, vast, right, though that might not be amenable, and this is two-dimensional. A picture is rarely two-dimensional, right? Image, for example. I'm just giving an image example because it's easier.
So when the space is warped,
yeah,
the image might get distorted, or it can be like features
Yes.
will be lost. Correct?
Yes, there's a possibility, at least in these sorts of networks, right, where everything mixes with everything, right? Here,
But still, the
X1 mixes.
problem when it comes to the classification, it can work well, right? When it
But
comes to
what are you
object
trying
detection,
to? What are you trying to do there? I mean, it could
Yes.
still work. I would say possibly it could work, but certain specific file level features which are very similar. Remember the Samoyed wolf problem, right? If you
Okay.
use this network, very likely that there are, they might not separate out in certain contexts, right? But in order to extract certain features that might tell you certain things common about a Samoyed, you might need a slightly different architecture. But it will solve some problem, but will it solve something that you actually want is another question.
so in the problem Samoyed versus wolf,
Mhm.
the classification would still be okay. But when we
Mhm.
go to the image where Samoyed and wolf are in the same picture, object detection using the same problem might not be feasible.
Probably, exactly. So that could be one situation where you said this might break.
Okay.
Yeah. So,
But in classification, it also fail. It can fail.
in classification also it might fail. It depends. Again, it depends upon the number of layers you have, the ways you do it. Let's say, for instance, you have a sufficient number of layers to actually crack that problem. There might be situations where the lightings could be different and still it fails, because there are certain levels that you cannot extract and certain features that mix with each other, which kind of give rise to both being different. So that is why these different types of architectures evolved, right, in the first place.
Sir, how to decide how many hidden layers do we need to
That's
solve
a empirical problem that is entirely dependent upon you. Yeah. So
for
that's
simple classification problems or
it
regression and
depends. It depends. Typically, a layer or two will work, but that's highly empirical. You got to play around with it.
okay. Problem to problem.
Problem to problem. Yeah.
So can I interpret that, suppose if it is a time series data or housing data, data, forward neural network is best solution.
Okay.
Suppose if it is an image, then anyhow we have to go to CNN.
So what's the question there?
I'm interpreting that for the time series, feed forward neural network is fine, and for the image where
no. So again, right, for time series data, probably we need to decide what you want to do, because if it's a prediction problem that you're trying to do, that is you're trying to predict what's going to happen next in time.
Yes.
It is important to understand or have, in some sense, a memory of what has happened in the past, right? For a feed forward network, there is no idea of memory currently, right? Because whatever goes in goes out at time step t, right? So there is no information of time step t minus 1 to some t minus capital T in the past. So we have to make sure that that information also is available to the network.
Because
and that's where we look at
very
different.
Why I had asked this question. So I am training my data set on the CNN. Now I have to go to the compute.
Yeah.
Automatically my infrastructure cost will be high. And simple regression model, the inference means we are also kind of benchmarking that what is the best techno-commercial possible solution in comparison to.
So we will look at this, exactly this, that there are ways to combine different models too, right? You don't have to just use one model. You can combine a CNN with an RNN. You can combine a RNN with a feed-forward network, and there are other ways. There are many sort of combinations, and that's why it's a very exciting field, right? There are, but you need to understand what is the problem at hand. It's not just about playing around with these networks, trying to see what works. That's not the best way. It's more about what is the intuition or feel that you have about your data. What sort of ways in which you think that you know that certain architectures have certain computational properties or capabilities, right? How does that help in solving the problem at hand? If you understand that, then you can come up with architectures that can help solve the problem better. And that's a big field of research in deep learning, right? Every time you see that people come up with new types of networks, new properties of the neurons, and that can, somehow enhance its capabilities suddenly. And that is coming up with a very deep understanding of what the problem entails sometimes, right? And knowing that if these are the capabilities, what are the limitations of such a network, and how can we actually improve that? And in fact, the attention aspects in transformers was a big part, right, of how the transformers were able to then even understand and keep track of many of the tokens in order to give you, context based answers. So the answer is it depends. Okay. All right, guys, we are slightly over our class time, but that was a good class. I was happy with all the interaction. So let's stop here today, and we'll pick up next week.
Yes, sir.
Sure, sir. And we had one more update from PGD patch, sir. So we
Yes.
tried to have a collective poll.
Yeah.
And 99% of us are agreed to have a class with 9 to 10 itself.
Okay.
So
Sounds
this is
good.
an update from our end.
But in our AI 23, it will become a big issue. Like we have,
But that's the point, right? Like I can't do stuff which is going to either we fix the class that we have, or it should work for 100% of the people. That's the point. So let's just keep the class that we have. You guys can come in a little bit later. Hopefully I will record all the classes, but I don't understand why a core course has been put in a place where you have these clashes.
No, but the issue is like sheet is very confusing. That whatever sheet we got, we like the last semester, whatever sheet we had, we thought that will be same. Like why time is changing? Saturday different and Sunday is different.
Yeah. Sorry,
For
one
the
second. I'll just stop this recording and then we can discuss. Because